Now that we understand the control tree, let's start connecting controls in more interesting ways by exploring the control components. We're going to hop around these a bit out of order based on their complexity. For instance, some of these control components are very easy to understand. Let's look at 5 pretty standard components. If you want to jump straight to a specific one, jump to its timecode as listed here. The control delay works very similar to an audio delay, in that once it receives a signal, it will wait a specified amount of time before allowing that signal to pass forward. You can set the maximum delay length here in the properties, and then adjust the actual delay length dynamically within Q-SYS. If you bypass the delay, it lets the signal pass through without any interruption. Unlike the audio delay, however, you can add multiple outputs to this component and customize the amount of delay for each of these. This might be useful for sequencing amplifiers to turn on or off, for instance. With a single button press, every one of these delays starts at the same time, letting you control when the signal is sent to each of the various outputs. Another fairly self-explanatory component is the control router. Much like an audio router, you can select from multiple possible inputs to be delivered to each output. You can customize the number of inputs and outputs as well as the selection style. Crosspoint buttons are radio-style buttons to select each input, whereas knobs give a single control that can scroll through each option, and combo buttons give the user a drop-down menu. The selection control style has no effect on the behavior of the router, but it does provide different types of controls that are available for your control pins. A simple example of a control router might be to deliver multiple different editable text fields into the dial string of a soft phone, so that you could quickly toggle between commonly used telephone numbers. The blinking LED is, spoiler alert, a blinking LED. You can adjust the period, which is the amount of time it takes for the LED to go through one on and off cycle, as well as the duty cycle, which specifies what percentage of that period is spent in an on state, which you could also randomize with the random button. If you disable this component, the button stops blinking. So what is the point of this? If you were just dying to get some flashy cabaret lights on your UCI to make it look like an old school Vegas marquee, then this is your component. Or, more importantly, you can use the LED output control pin to send an alternating true-false signal elsewhere in your design. You can find LEDs in many components in Q-SYS, but don't be fooled into thinking these are simple indicator lights. These aren't pointless lights in an old sci-fi spaceship.
Increase power.
These LEDs actually do something. When an LED is active, it has a value and position of 1 and a string of true, which you could use as a positive signal to activate anything else in your design. The same is true for a blinking LED, which you could use as a repeating on-off wave for anything in your design that requires a regularly alternating signal, such as sending a keep alive signal to a third-party connection, without using scripting. In some ways, you could consider the blinking LED to be a simplified version of the LFO component, which stands for low frequency oscillator. The LFO outputs a variable wave as represented by an output position knob. If you selected a square wave, that would effectively toggle the output between 0 and 100%, just like the behavior of the blinking LED. But if you chose something else for the waveform, such as a sine wave, you'll see the output rise and fall following the path of a sine wave. You could cap this behavior with the minimum and maximum knobs to constrict that oscillation within a customized range. There are a variety of waveforms to select from, which should give you plenty of flexibility if you need a variable repeating pattern for any reason. The last component we'll look at right now is the flip-flop. We've mentioned that trigger buttons don't have a value, string, or position, and don't really play well with toggle buttons. Well, the flip-flop is a tool you can use to take a momentary or trigger impulse and turn it into a latching on-off state. Think of the flip-flop as a light switch, and a trigger impulse is your finger. If your finger flicks on its own, there's no record of it doing anything. But if it flicked a light switch, then that light switch does have a state, which means that it has a value, string, and position. Looking inside its control panel, consider this state button to be the switch itself. While this is a toggle button, you generally won't interact with this button directly. The bottom two LEDs simply describe the state of the flip-flop. The out LED is on when the flip-flop state is true, and the not out LED is on when the flip-flop state is false. The three buttons at the top are all trigger buttons, which will affect the flip-flop states. The sets trigger will always set the state to true. The reset trigger will always set the state to false. And the toggle trigger will always toggle the flip-flop from its current state to the opposite. I'm going to say that one more time because this button can be deceptive. I know it's a button that says toggle right next to it, but this is not a toggle button. It's a trigger button which performs the action of toggling the flip-flop. Don't let that trick you. We have some simple exercises for you to complete in the control training worksheet on these simple control components, so go ahead and get your hands dirty and then come back for the next video.